Hello, Organic Chemistry 2342. We're going to continue on with our last section of Chapter 18. We're going to build on that malonic ester functionalization with the acetoacetate. Okay, so in this one right here, instead of having the diester functionality, we have the acetone section right here plus our acetic acid section here. And so we call it the acetoacetic ester synthesis. And what we'll end up with, instead of ending up with a carboxylic acid, like with the malonic acid ester, we're going to end up with a ketone. Specifically, if we use this particular one, we'll end up with a methyl ketone. Okay, but we can also end up with a diketone out of it. So let's continue on with this reaction. Of course, our first step is to use a base to remove our proton and our alpha carbon here, generating our enolate, which is our nucleophile. We can then use it as our nucleophile on any alkyl halide to generate our monosubstituted ester. Okay. Now, if we only want the monosubstituted ester, we could stop now and hydrolyze and decarbonylate, or if we wanted to have it disubstituted, we can actually then use a stronger base like T-butoxide here, and then we can add a different functional group or the same functional group, it doesn't matter, because we're doing it stepwise. You can choose which one you want, and then you can get the difunctionalized ester to get it to this compound here. And again, this could be your product you want, or you can even go through the acidic catalyzed decarbonylation to get to the monoketone. Okay. So if we want to get to the monoketone, we can do it. Oops. We're going to screen share again. If we want to get to the monoketone, what we can do is do what we did in the malonic acid ester synthesis, react our base with our alkoxide here, do our reaction to form our addition right here, and then do the decarbonylation to give us our terminal methyl ketone. Okay. So if we don't want a terminal methyl ketone, what we can do is we can do some other interesting things with it. We are also, in our first step here, we're creating a nucleophile. We can use that nucleophile to react with anything. So we've already learned in the previous section 2 that we can make these alpha halo carboxylic acid esters, okay? So if we were to use this as our substrate and make our enolate, our nucleophile to displace this, we will end up with a carboxylic acid on our alpha carbon, but we also have a carboxylic acid on our gamma carbon, on our beta carbon here, and this would make it our gamma carbon, okay? So if we form this compound and we hydrolyze it off, what we'll end up with is the dicarboxylic acid ester with the ketone still intact. And then if we went through that decarbonylation, this group right here will not clip off because it can't form that 6-membered ring. So what happens is we always will clip off this group and not the other group, because we'll be able to form that 6-membered ring. And so what we'll end up with is this gamma diketone, or a gamma carboxylic acid ketone. So we, again, since we are creating the nucleophile, we can use it in any other nucleophilic attack we want. So one of the substitutions we've learned about in chapter 17 is the nucleophilic acyl substitution. So once we generate our enolate here by our base, and we would typically do these reactions in an aprotic solvent, in a non-aqueous solvent, because we actually want to use the acyl halide as our reactant. So we can't have an alcohol or an alternative to ester, and we can't have water because that'll hydrolyze it to the acid. So in this case, we want to form the enolate in an anhydrous condition such that we can use that as the nucleophile to displace chloride here, giving us our acyl group attached to it. Now, once we have our acyl group there, we can then do what we did in the malonic acid ester synthesis, or the acetoacid ester synthesis, and hydrolyze to the carboxylic acid, and then we can decarbonylate. Notice this allows us to make a beta diketone compound. Okay. Notice beta diketone compounds were also used as the substrate in some of those other reactions where we can add additional functionality to that alpha carbon here. But here we're actually generating it by using an acyl substitution reaction like the ones we learned in chapter 17 to create a beta diketone product. Okay, so now that we've learned how to do that with carboxylic acids and the ketone systems, you don't have to have a carboxylic acid or a ketone. You can have any electron withdrawing group and that gamma and that beta position such that you can create that electron withdrawing and make those hydrogens acidic. So we can also have a ketone right here, an aldehyde, esters, amides, nitriles, nitros, sulfonyls, sulfates, sulfonyl esters, and sulfonyl amides. Any of these can be used. So you can have an unsymmetrical system as long as you have two electron withdrawing groups and they are have that alpha carbon in between them. You can make the compounds very acidic and do substitutions on them. So one example here is at the bottom where we have a cyano group as one of the electron withdrawing groups and an ester as the other electron withdrawing group. We can use the base here, just the alkoxide base, to generate our first substitution here. And then once we have our first substitution, these are actually acidic enough to use an alkoxide again to generate it and get our second substitution here. So once you form that that alpha carbon is, you make that those hydrogens acidic enough, you can use any of those functional groups. So let's see what kind of other things we can do. Now, instead of having that the carbonyl actually helping you create the enolate, we can do what we call an enamine synthesis. And what that means is we can actually displace that carbonyl with a nitrogen. And when we displace that carbonyl with a nitrogen, we can actually make an enol type derivative. So if we look here, an enamine is where we take a ketone right here and a nitrogen here, and then we remove water in the presence of a slight catalyst to generate our compound here. Notice this looks a lot like that enol. That enol is the nucleophile of our system as well. So if we, once we form that, we can have that search for any electrophile, and it can react with that as well. Note we can use any of these difunctional amines. Most of the time we use the cyclic amines to do this because it ties them back into a nice bow and makes them not very bulky, and so that we can do that reaction at that alpha carbon. Okay, so how can we use this in synthesis? Well, it's very useful in synthesis because when we do this, we don't have to have a carboxylic acid. We can do these in the absence of water. And so we can do it with other substrates we might not normally have. But the basic reaction is we take our ketone with our amine and heat it up with a little trace of acid. That'll form our enamine. Our enamine is now the, the nucleophile, and it can displace through SN1, SN2 type reactions to generate our substituted group at that place. Note it's only creates the enamine on one side, so it's only going to get a mono substitution. And then all we have to do is add a little water at the end of the reaction with acid to generate our free ketone. Okay, so here's the advantages of that enamine route. First of all, you only get monoalkylation. In the case of if we had a base like LDA, if you don't use exactly one equivalent of LDA, you have the possibility of deprotonating once in the alpha position, and then you have an opportunity to deprotonate in the other position, or doing multiple deprotonations, or even occasionally getting nucleophilic attack by the oxygen itself. So in the case of LDA here, we can, unless you make sure that your stoichiometry is exactly perfect, you're going to end up with all of these side products here. In the case of forming the enamine right here, because it just generates it in that perfect enol form, where it only has that double bond, it'll only form that once, and we'll only get a mono substitution on the system, okay? So what we can use is that enamine reaction to help us with the aldehydes. Remember, aldehydes gave poor yields in that initial reaction, so we always looked at esters or ketones to do this. We can actually use the enamine type reaction with aldehydes. What we'll do is we'll generate the enamine across the aldehyde portion here first, then we'll get mono substitution at this site right here. So we'll generate our double bond here in the middle. It'll do the mono substitution right here. And then we use the acid here to hydrolyze off the enamine. And we get perfect mono substitution in good yields, okay? So just like before, where we're using it as the electrophile, that means we can use it on any other reaction. For example, if we wanted to use it against an acyl halide, we can actually, again, generate it in the absence of water. We form our enamine and isolate it as this. Now this is our electrophile. So once we form that, we have our electrophile attacking our acyl halide, and then chlorine kicks out from the reaction, generating our enamine salt here. Then once we hydrolyze that enamine salt, we end up with a beta diketone here by just perfectly adding a single acyl group to it. Okay, so that makes it really synthetically useful for taking an enamine. Imagine making a beta, using an aldehyde instead, so you have an aldehyde ketone in the same compound. Okay, so that's the utility of making those enolate ions, using them as nucleophiles, and reacting them to form a variety of different chemical structures.